Okay, so if you if you know that if you have a charged particle and you need it to go towards some place, then you put a negative charge on that location, goal location, and then you have the positive charge getting attracted to the negative charge, right? That's how you would do it with something which has uh, a charge. Now that basically negative charge creates a potential around it, and that potential sort of is attractive. So if you want the charge to go from here to here, you will basically put, I think the potential lines are something like this. So it'll basically uh, go from positive to negative. So there's a potential field created by the charge. Um, the goal is the robot. Okay, now, but if there's an obstacle, then you want to steer away from that obstacle. So if you, instead of having, what you could do is for the obstacle is, let's say there's an obstacle here, you could put a charge which is also positive on the way wherever the obstacle is, and which means that now that positive charge will create a field around itself, and that's repulsive, and that repulsive field will sort of make the robot avoid the straight path. It'll instead have to take a turn, right? So that's the idea. So create potential fields, not real, they're artificial fields, and those fields somehow we need to relate those fields with the actual motion of the robot. That is, essentially we have an ability to control the robot. For a car, it is the velocity. For a manipulator, it could be the torques and so on. So that's the idea. Introduce sort of potential fields. So we'll define a attractive potential field, ATT, and then we'll define a repulsive potential field, and then the sum. So when you want to do something like what I've shown in the caricature, you want to sum them up so that way they'll all take care of the positive, negative charge and steer things away. So the net field is attractive plus repulsive. So you get that first. That's the first step. Next, we need to figure out how we can make this move. So what we do is the force, and this is something which comes from physics, is always the gradient of uh, u. Okay, so I'll write it as del u of q. Here, this gradient operator is basically depends on the degrees of freedom. So if, for example, if there is an x and y, then the gradient, you'll take that gradient with respect q with respect to x and q with respect to y. Think of this as a Jacobian effectively. This is an equivalent is the Jacobian. And we'll see what that is in a bit, but this should actually be negative. So you always go towards the negative potential, right? So for example, if you drop, gravity is one example of a potential field. Okay, gravity is set up in such a way that anything dropped from the sky will always find its way down because the potential is essentially driving it towards the negative of that, so minus g, right? Minus mg. Okay, so that's that. Now, how do we create these forces? Well, sorry, this potential field, because computing F is straightforward. So this is something which we'll use certain fields which are popular, and then you can come up with your own. But these are the ones which are more popular. So I'm going to give you two examples of attractive fields, and we'll plot them, and then we'll give an example for repulsive field. We'll plot them, and then we'll look at how to combine those fields to generate motion we care about. Okay, so let's do these individual fields first. Try to understand them. Make some plots. I'll give you the formulas, and then go from there. So first, let's do attractive potential field. Okay, so I'm going to talk about two attractive fields. Number one is what I would call the conic potential field. Okay, so what that looks like is U attract equals, now I need to create some notation. So let's say that Before we do that, let's assume that this is a point mass robot. It's at So let's say it's at position p, which is a function of q. So this p is its position. This q denotes the degrees of freedom. So for example, if it was just a point in 2D plane, it'll have an x and y coordinates, right? For a two-link or three-link manipulator, it will be something like L cosine theta, L sine theta. So it's not necessarily has to be simply as x and y. It could be something more complicated depending on the type of system you look at. So that's the position. And remember, we're trying to get to a goal. And let's say that the goal is QF or QG. So this is okay. So we are trying to create this field. And one way of doing it is to just specify the distance between P of Q and P of QG. Okay. Now, when you take the distance, you'll, let's say, just a 2D particle, it'll be x minus xg, y minus yg, right? It'll be a vector. But potential field is always a scalar. So what we do is we'll actually use the magnitude. Okay. Another way, this is one way of writing it. Another way of writing it is P of Q minus P of QG dot P of Q minus P of QG. So what the dot product does, it basically takes the magnitude, but since it's the magnitude, it will be the squared, so you need to take the square root. So these are the same things. Another way of writing that term, the norm, this is the norm, is that formula. So you'll take x minus x square plus y minus y square and take the square root of the sum. Okay, so that's the conic field. I'm going to, well, let me just plot it here first, but then I also have a code which will plot it for you. So if you draw this field and just, let's do it in one dimension. It's easy to understand one dimension. U attractive, and let's say this is a function of Q. Then when you make a plot, if Q G is here, you'll see that this curve will look something like this. Okay. Uh, so the force is minus gradient of U attractive will actually be P of Q minus P of QG divided by magnitude of P of Q minus P of QG. So how do I get this? Well, it's easier to do it with this expression. If you take this expression and if you take the derivative with respect to Q, then it's basically, maybe I should just derive it. This should be, think of this as x dot x, just derive that. So this is how you get it. If you have x dot x square root and you want to do d attractive, and so this is basically a function of q, then du attractive, dq. So it's x squared. So the derivative of x squared is So when you have the derivative of something like this, it's always square root x cube square. Okay, and then we need to take the derivative of x of q here. So that will be dx. That's right. Um, Something is not right. This is oh yeah, let me think. So this is basically using calculus. Essentially, you need to first take the derivative of x cube, and for that you use physically the chain rule. This is yeah. Let me try it this way. What if you start directly from this? Yeah, the derivative of that is going to be easier to see it if you write it like this. It's much easier to see it. Why don't we just take an example into it? That's an example. So that's one way of writing the potential. So if you take the derivative of this, so you need to do du dx y, so the Jacobian. So you'll have two terms to it. So when you take the derivative with respect to x, you'll have and then you take the derivative of this whole term. It'll be 2x minus xg, comma, same for y. So when you write it as a vector, you'll get two. I'm missing something. Sorry. This is half, right? So this should be 1 divided by 2 here. The derivative of something raised to half is half times, oh my God, let me, almost there, I'll get it. So the derivative of something like this is half x minus xg square plus y minus yg square. So it's going to be half minus 1, right? Derivative of is n x n minus 1. I use that formula. So n is half. So the half is here. And then half minus 1. That's n minus 1. Okay. So that's that. That's the first part. It's not complete yet. Then I need to take the derivative of everything inside the bracket. That's the chain rule. So twice x minus xg, comma, twice y minus yg. So that's it's going to be like this because I'm going to take the derivative of with respect to x and with respect to y. Basically, it's the Jacobian. So what I get here is I'm just going to take that distributed over these two terms. So I'll get twice x minus xg divided by 2 square root x minus xg square plus y minus yg square, comma 2y minus yg twice x minus xg square plus y minus yg square. Okay, now what will happen is this 2 will cancel with this 2. So that's du, and then the force is minus du. I'm missing a minus here. There should be a minus. No, I guess I'm. There is there a minus n minus 1? I think it's fine. So it'll be minus du dq will be uh, minus x minus basically this whole thing. Minus and minus. Need this. Okay, to cut a long story short, what you get there is basically the vector, which is, let me pull this out, minus out. This is a vector, x minus xg, I component, y component, divided the magnitude of the vector is basically the unit vector. That's what we will get to. So the force is the vector, in this case it was x. What did I use? So it's minus vector divided by norm of the vector. That's what we had. So vector x minus xg, y minus yg, so x and y component divided by the norm. And that is essentially what I wrote down. Did I write it down here? So it's essentially the same thing. The vector divided by a norm of vector. And that is what we got here, vector divided norm vector. So it is, in this case, it's going to be P of Q minus P of QG divided by magnitude P of Q minus P of QG. So the main thing to understand here, it's basically the force is a unit vector. The magnitude of F, so note the magnitude of F is equal to 1, right? If you take this F, which you see here, and you take the magnitude, so you take the x component square plus y component square, and then sum it up, you'll see that it is 1. Okay, and because this magnitude is 1, because this is 1, if you look back and see this field, you'll see that the slope is 1. This slope is 1. That's important. We'll come back to it. And what happens is there's an interesting thing, which is right here, there's a kink. Okay, F not defined. So this potential will have a real problem when you go close to the goal, because one side it's +1, other side it's -1, and what happens at 0 is not clear. So what people do is they actually fix it in this fashion. For the conic potential, they'll write, so at Q equals QG, F is not defined. So what they'll do is they'll say that F equals the gradient of U attractive at Q not equal to QG, and then it is equal to 0 at Q equals QG. So when it reaches the goal, you should not find the force, because then it's going to be something weird. Okay, so that's how people will do this. Now that's one potential. The second potential we'll look is the parabolic potential. which will actually not have the problems of this potential. Okay, done. The second potential we'll look at is the second one, parabolic potential. Okay, so here U attractive is written as half psi. It is just a parameter which can be used to tune, it's a constant, times the magnitude of P of Q minus P of QG square. Okay, so the only difference between this one and that one is that square. This is the most significant change. So if you look at conic, I have it here. Yeah, if you see this one, it doesn't have the square. So this one has the square. That's the only difference. Okay, and that has big consequences, as you'll see. So if you write it this way, you can make a plot similar to the one I drew earlier of U attractive as a function of Q. You'll see that it'll actually look like a bowl. Okay, with the bottom of the bowl here being QG. It's so there's a change in shape. It's going to be parabolic because it's a second order equation, and the first one was first order. Okay, so if that's the potential, what's the force? Force is minus du dq, which now in this case you could write it as, okay, this time let me try to attempt to do it without doing what I did earlier. So the magnitude is P of Q minus P of QG dot with P of Q minus P of QG. So the dot is another way of writing the norm. So when I take the derivative, so this is a, let me just write it down. This is a constant. I can pull that out, and there's a half, which I forgot. So minus epsilon divided by, so equals minus psi divided by 2. And let me take the derivative of this. So derivative of this would just be P of Q minus P of QG. Okay, so it's basically this term plus this term square. So square of that should be, actually this should be a 2 here, because I think this is x, this is x square. The derivative of x square is twice x, so 2x. So this 2 and this 2 cancels off, and you're left with force, which is psi P of Q minus P of QG. Okay, so that's the formula. So what this term here is basically the distance between the point Q. Okay, remember the robot is traveling along this. So it starts off, let's say here. So the distance is going to be, so it's here, this is the distance, right? Then the robot comes here, this is the distance. So it's basically saying that the bigger the distance, the bigger is the force, and smaller the distance, smaller is the force. That actually is a problem. If the robot is very far away from the goal, the force pulling it towards the goal is going to be very high. And if the robot is very close to the obstacle, the force is going to be small. Okay, this is different from what we got for this field. Here we saw that the slope was 1. So no matter where the robot is with respect to the goal, its force is always going to be 1. It's going to come towards the goal with a constant force. but there's a problem at 0 or QG, right? Its slope is not defined. If you look at parabolic, there is no problem here, no issues, because it's a smooth function, it's a curve, right? So you can find that. So what we see is that the parabolic profile has a problem far away from the origin, far from QG. The force is large, while that problem is not there for the linear profile or the conic profile. And then very close to QG, the conic potential is a problem with the derivative, but there's no problem with the, what do you call, the parabolic profile has no problem. Conic profile has a problem. So what people do is they mix the two. Far from the goal, QG, you want to use the conic potential because the force is constant. Okay. While close to the goal, you want to use the parabolic profile because the force is defined at close to QG. So that's the rationale behind using these two fields. So let me write all that down. So conic constant force away from QG, force is not defined at QG. Parabolic force is defined at QG. Force is large. No, or force is proportional to distance from QG. Okay, so these are the advantages. This is an advantage. This is an advantage. This is an advantage of this profile. There's an advantage. So we use best of both worlds. So we combine conic and parabolic. So choose a distance d from QG away. Okay, if so, let's say if so if robot is far is at a distance greater than d, then use conic potential. If robot is at a distance less than d, use parabolic potential. So I'll write down the formula for that. Essentially combining the two. This is what it'll look like. So third one, combined conic parabolic field. So the U attractive is written as follows: half psi magnitude P of Q minus P of QG. Need more room. Okay, so this you'll do this if and only if P of Q minus P of QG, this is the distance, is less than D. And you can use D psi, but there should be a square here. P of Q plus P of QG minus half psi D square if P of Q minus P of QG is greater than D. These are conditionals. Okay, so there is this term, which is, why is this term coming in there? So why do we need that? Well, it's a constant, first of all. And the reason why you have this constant term is because you will see that at the boundary at exactly the value D, you need to ensure that the U attractive is continuous. If you don't have that half D square, half psi D square, then it'll become discontinuous. You can test it out. When you have this distance is D, you will get half psi D square, right? When you have this coming in at this expression, if you put this whole thing is equal to D, you will have D psi square minus half D psi square, which is half D psi square. So half D psi square will be the same as half D psi square. So it will be continuous. Otherwise, you will have a discontinuity. You'll see that the robot will jump at that point if you remove it out. Okay, so that's that. And then if you want to find the force, all you do is take the derivative of the expression shown there. So you'll have two terms here, depending on the region you stay. So it's going to be psi P of Q minus P of QG equals minus D psi and the vector. So it'll be P of Q minus P of QG divided by P of Q minus P of QG. So this would be when P of Q minus P of QG is less than D or equal to D. And this will be when P of Q minus P of QG is greater than D. Okay, so just cases to plug and play. Okay, let me show you what those profiles look like. Yeah, question.
For the parabolic potential, why is it so bad that the force is large distance?
Because it's the force is the, if you look at, okay, so this is the force. It's basically it's basically the magnitude of the distance. So the force is a vector, but if you want to find the magnitude, you basically take the distance. So you take the norm of that. So if you keep, it's best illustrated. It's basically the distance from QG. So initially, if you have Q is here, this distance is, the force is going to be proportional to this distance. Then it'll be this distance and so on. So think of it like a spring. The further away you are from the equilibrium point being QG, the bigger is the force, because it's like essentially doesn't it look like a spring force? Look at this.
No, that makes sense. Yeah. I'm just wondering, like, what, like in it's like real life scenario.
Oh, this is just, the fields are artificial fields. Okay. They are not a physical quantity. They are fields. What we do is, just to make a robot go from point A to point B, we think of putting a rubber band with this field between the robot and the goal, and then let it go. So if you put a rubber band, it'll go much faster if you put it. I mean, it'll go faster the further away from the goal, right? And as I said, the rubber bands, you create those rubber bands. It's not that there are rubber bands or springs between 2 points. We've not yet got to the point where we're using this to. We'll get to the point where what we say force, how does it translate to an actual control in the robot is coming next. Okay, good question. So let me just show you what these profiles look like. First I did was just the attractive fields. The goal is, it's called XF here, is 5. There's some constant 10. And then quadratic and conic. I have done one-dimensional plot first. It's essentially the same as what I had shown on paper, right? So quadratic and conic with this 0, the slope being not defined. It's actually more interesting to do a 2D plot. 2D plot, you have the luxury of doing this for something which is moving in 2 dimension. So there are actually 4 plots which throws this plot. Okay, so first of all, this is what the conic and quadratic will look in 2 dimensions. So XY is, of course, the distance, and the vertical is the potential. So you can see that it's a cone shaped. It's like a bowl. Let's me close this. I think it'll, okay. Okay. Then you can also do a contour plot, which actually is kind of what people normally do for such things. When you have like a hill, you take slices which are at the same height, and then you basically plot them in 2 dimensions. So it's a 2-dimensional plot, but you basically show the slices based on height. So if you look at the slices for conic, you'll see that those are equidistant. So the hills are same height. So you'll see that those are sort of like concentric circles with the same width, right? Here, if you see, it's much different. It's basically going to be similar to that, but as you get closer to the goal, you'll see a big patch which is close to 0. Okay, so that's where the force is. It's just saying that the force is not constant. The force is going to be large here and go down. In fact, the force goes 0 very quickly here, so it might actually have a hard time going to the origin because the slope here, remember, is always 1, so it's always going to take constant force. But if the force goes close to 0, going to the goal might take forever. That's something to think about. Okay, so that's that.